So what I'd like to do with you now is walk through an example of how logistic regression works. And so hopefully this is making it tractable for you. Remember, we're really focused on applied statistics here rather than theoretical statistics. So let's have a look at an example and see if we can make sense. So what I'm going to do is walk through the model setup. The context that I'm going to use for this is a transport example, which is again kind of the space where these kinds of things are used, and then focus in on the bits that we're interested in. All right, so here I'm just reading in some data. This is I think this is a data file in here. I'm just, for completeness, showing you what I've got reading in here. So this is my variable. This is the travel time for a car. This is travel time for a bus, and this is a variable I've created called the difference in time. And this is the coding. So it's car. If you took car, it's 1. If you took the bus, it's 0. And you can see here, if we read across here, so it says time to get where we're going by car is this long, time by bus is this long. The difference, which is this value minus this value, and then how we went there. And so I've coded bus as 0 and car as 1. And that's what I've got here explaining, okay? So these are the variables we've got, time in minutes. And this is the created variable d time. All right, so it's not a, pretty simple data set to have a look at. And you would always want to do that when you read it in, use the head command and the structure command to have a look at the data. So let's really just make sure that we can follow the coding. So this is a really important step for you to understand your data. So you might want to jump to estimating some models, but the way to read this is that for this case, the bus is faster and the person travelled by bus. Here again, the bus is slower. It takes longer on the bus, but the person has still taken the bus. And this one over here, this time the bus is much longer than the car and the person has taken the car. So you can imagine that there could be some income thing going on here as well, or maybe you're coming to uni and you can't get a park anyway, so you may as well catch the bus even though it's slower, right? Because you'll just be driving around in the car park. So you really need to spend a bit of time coming to terms with your data. Also important step is to plot the data. So let's have a look at the plot we've got going on here. We've got a nice axis label, which is making it nice and clear to us to say, okay, what's going on? I've got relative time, so I'm using that d time variable. I've got drive, or car equals 1, bus equals 0. I put a little nudge on this line so that it doesn't cover up my dots exactly. You don't have to do that. You can see here is the when they're equally the same distance, and I'm just trying to make it easier for the reader to understand. Okay, it's relative time, and I could have coded it either way, and because of that, way that you could code things differently, it can be helpful to make it quite clear in your pictures what's going on. All right, so I think that's now we understand what's going on, and generally when it's quicker, so this is a logic check for you. Generally when the bus is quicker, we take the bus. Generally when the car is quicker, we take the car. So you want to make sure that when you create a plot that it's sort of logically consistent, or you have a good reason for thinking that it might be doing something different. Now let's have a look at our model. Now the first thing, recall that, okay, so we know when we estimate this model, could have a linear probability model. So we've got 0, 1 data. This is not going to be the model we want to settle on, but I'm just showing you that's the model that we would estimate. And recall that we get all this stuff. So if I just paste in all the R output, it looks quite a bit of a mess. So I'm going to remember that there's all this output comes, but I'm just going to be taking a snapshot of it when we go through these slides. So we've got something like this. Okay, so this would be my summary regression results table, 21 observations, not really interested in the intercept. I've called this relative time, so I haven't just called it d time, which is the variable name in the data file. I've given it a meaningful practical name, and you can see here that this variable is statistically significant at the 0.1 level. How much of the variation in the data is explained? Okay, a reasonable amount. So it means that I've got something like this. This is the kind of thing that we would use to explain our results. But this is what the fitted model would look like. And remember that it's got this problem here that we predict outside the 0,1 bound. And just generally, we're just a bit uncomfortable with doing that, especially if we know some ways that we can do better. All right, but that's what the linear probability model would look like. What does the logit model look like? Well, it turns out it's not a really big step for us. We changed the LM to a GLM for generalized linear model. And because it's generalized, there's actually one more step. So we just need to say that we're using the logit as the link function. So what does that mean? That's the function that maps our dependent variable to those linear predictors. So we remember that first lecture part where we're talking all about these transformations. So that's all we need to do. So the step to go from linear regression to generalized linear regression is as simple as this. We change one point from LM to GLM and we specify the extra family. All right, and that's all we need to do. All right, but remember, similar to linear regression, when we started making transformations on the dependent variable, we know that we have to be careful about how we interpret this guy down here. So we know that this is significant. Okay, that's good from our point of view. We think that that's probably a logical story here, that the relative time on the two transport systems is going to be driving decisions. You can also see that with generalized linear models, they don't spit out an AIC value. They'll typically spit out a log likelihood and an AIC value. I'm pretty ambivalent about what you report for these kinds of things. It's typical to report the log likelihood though. And this is the curve that's fitted. Okay, so I haven't said how we interpret this guy here, this slope coefficient, other than it's significant at this point. But what we can do is just say, well, what does the curve look like? Remember that this guy is controlling we can slide our curve along depending on the intercept, and this is going to control the shape. And if you think back to the shapes that we looked at, you can see that this is going to be relatively flat. All right. Obviously, you can change this around by what you put on the horizontal scale, but it's not going to be a sharp transition. That much we know. And that's really what we see here. We see this relatively smooth transition. When we're out here, predicted probability is very close to 1. It's very clear. Down here, it's very clear. There's a bit of ambiguity here in the middle. So our line is, we just sort of feel that that's a better fit to the data. Sure, there's these guys out here that are out there, but it just seems a better fit, and we don't have these predictions outside the 0,1 bound. So a small change to our model gives us a nice fitting curve. Of course, it is, what are we doing on here? So if we just get the predicted value, it gives us these predicted values. Now, what are these values? These are values on a log odd scale. Now, even I struggle with trying to think about what values mean on a log odd scale. I can kind of do some rough, if you work with them enough, you can do some rough numbers. But what have we got here? We know then when d time is equal to 30, then we're getting this predicted value that's positive. And when d time is negative 30, we're getting a strong negative number. And around 0, a number, sort of relatively close to 0. But again, very hard to interpret what's going on. Fortunately, it's quite a little bit easier to get some values that might be intuitive to us. So these are predicted probabilities. Remember that we're modeling this as if it's a probability. So when we put it on the response scale, when d time is equal to 30, it says the predicted probability is 0.79. What does that mean? That is the predicted probability that we will travel by car. This means that if car is a faster transport, it's likely that we will pick car. Down here, d time minus 30. That means that the bus is 30 minutes faster than the car. When the bus is 30 minutes faster than transport by car, the predicted probability is 0.13. So we would say, predicted probability less than 0.5 means that we would allocate that person as for our prediction and say, well, in practice, they're going to take the bus. Similarly up here, a predicted probability above 0.05 means that we're going to predict that they take the car. All right, so you can see it's actually not that hard to get values on the predicted scale using this slight, predict, and one slight extension to what you've learned for linear model predictions, which is to add this type response term at the end. So that's not too much of an extension for you. I said previously that the marginal effects change. And the marginal effects, how do we get the marginal effects? The formula for getting the marginal effects is in the R script, and it's a little bit complicated. So what I do is I say, if I want to evaluate at 0, I go half a time period after and before, okay? And I have my change between these two time periods. And that's how I get my predicted probability. The marginal effect at time 0 is the difference between this guy and this guy. If I want to evaluate at 20, I go to 20.5 minus the predicted value at 20.19, and that gives me the marginal effect. So the marginal effect is the change evaluated at 20 minutes, and similarly if I was to do it at 30. So what I guess you can see here is when these are all far away from, the midpoint. When I'm down here, the marginal effect is very, very small. So it says when the bus is already much faster than the car, the impact of a marginal minute is pretty small. All right, and similarly over here, when the car is already much faster than the bus, well, 1 more minute doesn't make much difference. But the marginal effect here around 0 is actually quite a bit high. So here it's 0.006, so 0.1. So here we've got different marginal effects. The highest marginal effect is actually around this 0 point here. So that kind of makes sense, right? That's the point where it's close between switching, like is the car faster or the bus faster? If you just switch from going from the bus being a little bit faster to the car being a little bit faster, so that relative time term would change, it makes sense that that might have a more substantive impact on your decisions. Final thing here is this 50% support point. So what do we know about this 50% support point? Beta 0 divided by beta 1. So it says that at the 50% support point, we get an estimate of 4.47. Well, what does that mean? It means that when the car is slightly faster than the bus, 50% of the people will choose to take the car. So it tells us something like on an equal footing, there's a slight preference for bus travel, and that could be because of cost, could be for a whole range of other reasons. The way that we get this, so we know that that's the formula, and we just use this function called the delta method function. So we say, this is the function. We call it on our GLM object, which is here, which is called logit1. I just rename the parameters here, the covariance matrix that we want from logit1, and away we go, and it will spit out our results over here. And the main one that we're looking at here, right, this value here. And remember, the interpretation of that depends on how we coded the data. And from this, when the car is slightly faster, we have only then will we have 50% of the people traveling by car. But from these uncertainty bounds or the standard error, we know that that estimate is quite imprecise. So that's an overview of working through a logit model in a practical sense, and hopefully that's made some of the concepts more concrete for you, or at least it's some preparation for when you get into the lab.